Okay, so this is the first lecture that we will, in which we will discuss the notion of vector spaces. And before we go into vector spaces, we will briefly discuss what is a field. So intuitively, a field is just an algebraic object which facilitates addition, multiplication, subtraction, and division. Formal definition, if you haven't seen this kind of thing before, will look a little bit of a mouthful, but we'll see important examples, and I think we'll be fine. So here is the definition. A field F. A field is a triple. Field is a triple where F is a set. Sorry about that. F is a set plus is a binary operation. It just means that it is a function from F cross F to F. We call it the addition, called addition. And this has nothing to do with the usual addition, or may have nothing to do with the usual addition of real numbers or rational numbers or anything. So this, it's equipped with a binary operation called addition and another binary operation which we call multiplication. Which such that some basic properties that we would require of these two operations would be satisfied, such that, so we would definitely demand associativity. Associativity, which means associativity of addition as well as multiplication. So we want this to hold. And A dot B dot C equals A dot B dot C for all A, B, C in F. Now, before I should have said this, perhaps I should have made a comment that we write A plus B in place of plus of A comma B, and A dot B in place of dot of A comma B. See, syntactically, plus is a function which takes a pair of elements in F to an element of F. So it's kind of meaningless to write B plus C or A plus B or any such thing. But we just, when we write A plus B, what we mean is this. In fact, we will not even write dot. In fact, we just write AB to mean A dot B. So I hope that does not cause any confusion. But please do not confuse this plus with your usual plus that you're familiar with, the addition in real numbers, or this multiplication, the multiplication in real numbers, rational numbers, or anything. So we require this associativity property, we require commutativity. Which means that A plus B is equal to B plus A, and A dot B equals B dot A for all A, B in F. And we require the existence of identities, additive and multiplicative identities. Additive identity and multiplicative identity. So let me write it this way, multiplicative. Identity, which means that there exists an element which we denote by 0. There exists an element 0 in F and an element 1 in F, such that 0 plus A equals A for all 0 plus A equals A, and 1 dot A equals A, again for all A in F. Now this might be a little bit confusing. What do I mean? There exists 0. I'm calling it 0, so of course this should be true. What I mean is that there is an element in F which has a property that if you add it to any element of the field, then you get back that element of the field. And we denote that, well, a priori, any such element by the symbol 0. But one can easily see that any such element has to be unique. So this is called the additive identity of the field, because additively it is behaving like identity, it is not changing anything. Similarly, there we insist that there is an element which we denote by a 1 in the field, which behaves as a multiplicative identity. If you multiply it by an element, it does not change the element. And again, you can see that it has to be unique. So this is an axiom that we insist on in the definition of a field. And we insist on inverses, again, additive and multiplicative inverses. Additive and multiplicative inverses. Which says the following: for all A in F, there exists an element which there exists an element B in F such that A plus B is 0. A plus B is the additive identity of the field of F. And for all non-zero elements of F, there exists a B in F such that AB equals the multiplicative identity of the field. Of course, this is just mimicking your usual addition and multiplication in real numbers. Just a bit of notation, we write this thing as F star. Further notation, we write, one can easily see that this guy has to be unique. Given an A, there is only one B. In fact, we insist that there exists a B, but one can easily show that if there is one, there is going to be only one B such that this is satisfied. Similarly, once you're given a non-zero element and you can find a B, we insist that we can find a B such that this happens, and one can easily show that there is going to be only one such B. So we denote, we call this B the additive inverse of, we call this be the additive inverse of A and this be the multiplicative inverse of A, and we have the following notation. We denote the additive inverse of A by minus A. and the multiplicative inverse of A by either 1 by A, or you can keep this simple. These are two very common notations. And lastly, we insist on distributivity. So these addition and multiplication should interact in some way. Distributivity. It says that for all elements A, B, and C and F, we have the multiplication distributes over the addition. So this is quite a long list of axioms. For the first time, if you see, it may seem like a very bizarre thing to even do. But basically, this is axiomatizing the usual addition and multiplication, the ones we are most familiar with. So when we see any abstract definition in mathematics, we should reinforce our understanding by examples. And there's no point trying to remember these axioms, but they become natural as we go along. And here is the point. Basically, we need to see some examples. So example, the most familiar field, I would say, is the field of real numbers. And this is one of the most important fields for our purposes. So it's real numbers. So let R, this is the notation for the field of real numbers. Let R be the set of real numbers. Set of real numbers plus be the usual addition and dot be the usual multiplication. Then it is just a simple check, and it's a good exercise to do it. This is a field. And a lot of the times, in fact, almost all the time, when we say that, we have defined field as a triple, but we'll abuse this just by calling F a field, even though F is just a part, just a component in this triple. By abuse of language, we'll just call F a field. So we don't, every time we refer to a field, we don't necessarily prescribe what was the addition and what was the multiplication. We just say, like, consider the field F, right? So that's just for ease of conversation and ease of writing. Okay, so this is a field. We are each one of us is familiar with it. Another very important example of field is the field of complex numbers. So again, let C be the set of all the complex numbers. And again, the same story. So we have plus as the usual addition, be the usual addition, and dot as be the usual multiplication. And then one can check that this is a field. And another very important example is the field of rational numbers. So here is the notation. Let Q be the set, all the rationals. And if you add two rationals, you get a rational. You multiply two rationals, you get a rational. You invert a non-zero rational, you get a rational. You invert a you take the additive inverse of a rational, it's again a rational. So this thing is a field. Where again, this is your usual addition and this is the usual multiplication. Another class of very important examples are finite fields. Finite fields are precisely those fields which have finite cardinality. All of the examples that we've seen are infinite. R is infinite, C is infinite, Q is infinite. So they do exist finite fields. It's non-trivial, I would say, somewhat non-trivial proof that finite fields of prime cardinality exist. I will not go into the details of these objects because most of linear algebra, to appreciate most of linear algebra, you just have to work with real and complex vector fields. And I would encourage, if this is the first time you are reading or learning linear algebra, that throughout the lectures, one should just focus on these two examples, the real and complex numbers, and sometimes one can even think of rational numbers, perfectly fine. I would say this is the most important one, and this is the somewhat lesser important one. But linear algebra is also very important for finite fields, and yeah, one should perhaps keep that in mind. Okay, and let us just see one non-example. This is not a field, it's a set of integers. The set of integers with usual addition, multiplication is not a field. This is simply because you can't invert every integer. If you take an integer, let's say 2, the multiplicative inverse of 2 does not exist in the integers. So it's not a field. The multiplicative inverse of 2 is half, which is not an integer. So that's that about fields. And now let us go to the definition of vector spaces. Again, this is going to be a very abstract definition, but the motivation is the following. A vector space is supposed to be a mathematical object which allows for scaling and it allows for addition. And the scaling and the addition operations, they behave well with each other. That's the idea roughly. Let me give a definition proper. So a vector space is a quadruple where V is a set, F is a field. So when I say F is a field, F already comes up with its own addition. So this is admittedly going to be confusing. But F comes with its own set, own plus, which I have just subscripted to so that we do not get confused with this plus, and its own multiplication so that we do not get confused with this guy. So V is a set and F is a field, and plus is a binary operation which we call addition. We call this addition of the vector space. One should not confuse this with the addition of the field. And a scaling operation, which is defined from X cross V to V. So this is also called the scalar field. The scalar field of the vector space. Given a vector space, you have it is always over some base field. Yeah, I should call it base field. And you can scale elements of the vector space by the elements of the base field. So you pick a vector V and you pick a scalar A, and then this multiplication out pops a scaled vector. And you can add vectors. Of course, we need to put some axioms on these two operations, plus and dot. These are the axioms. First is associativity. So for all u, v, or rather, let's not write it this way. We have u plus v plus w equals u plus v plus w for all vectors. The elements of the vector space are called vectors. We have additive inverse, additive identity. It's the same axioms that we insisted on for the field, the axioms for addition. Additive identity says that there exists a vector, which again we confusingly refer to by 0, such that 0 plus v equals v for all v in v. So do not confuse this 0 by the 0 of f. We use the same symbol for them. It's good to use the same symbol for them, but yes, if you're seeing it for the first time, it can get confusing. We want commutativity. Which says, of course, that u plus v equals v plus u for all vectors u, v, and v. And finally, additive inverse. That for all vectors u in v, there exists a vector v in v such that u plus v is 0. And we denote, so this is called the additive inverse of v. sorry, U. This guy is called, one can easily check that this is unique. So it is called D additive inverse of U. And we denote this by minus U. So it's the same axioms that we insisted on for a field. Whenever we have addition, we insist on these axioms. Whenever there is something we want to call addition, we insist on these axioms. If you know what an abelian group is, you recognize that all we are saying is that V along with plus forms an abelian group. But we don't need to know about abelian groups at all for this course. Okay, now so we have just dealt with these two, dealt with this guy in relation, what is its relation with V, but there are more things here, so we need to mention what are they, what do they have to do with this quadruple. So we have other more axioms. We have kind of I don't know what to call this axiom. Maybe I'll call it scaling identity or whatever. Let's just put a dot here. It says that 1f, which is the multiplicative identity of the field, when you scale any vector by it, you get the same vector back. And we do not write 1f, we will just write 1. Notationally, that's much neater. We have associativity of scaling in some sense. So what is this left side? This left side says that you have a vector v and you have a scalar b. Scalar b meaning it's in f. Vector is in capital V, this is in capital F. You scale your vector by b, and then you scale the resulting vector by another scalar, which we have denoted by a. You can do it in a different way. You can first multiply these two scalars and then you can scale v by the resulting scalar. Again, for all a, b in f, and v in v. We insist on this associativity. And now distributivity, which is a dot u plus v is what you guess. Again, for all a in f and u v in v. And this another counterpart of this distributivity is that a plus b dot v. Now note that this plus is really the addition happening in the field. A and b are elements of f, and this addition is happening in the field. Do not confuse this with the addition of the vector space. And this dot is the scalar function, which takes a pair, which first component of the pair is the element of the field, and the second component is the element of the vector space. It produces a vector, and with this axiom, this should be satisfied. For all a, b in f, and b in. So these four axioms, in addition to the previous, these four axioms plus these four axioms is what defines a vector space. When these 8 axioms are satisfied, we call this quadruple the vector space. And the elements of V will be called vectors. The elements of F are called scalars. This is called the addition. This is called the scaling. All right. And let us just note a simple thing. Note that if you scale a vector by the additive identity of the field, the zero is in the field, not in the vector space. There is a zero in the vector space, but this zero denotes the zero of the field. So what is this going to be? This is, of course, 0 plus 0 dot v, which is by distributivity rules that we just discussed, is equal to that. And now if you add the additive identity of whatever this guy is on both sides, you'll be left with 0 equals 0 plus, or rather, let me write it, 0 dot v plus 0. And this 0 is the 0 of the vector space. Whatever this vector is, we have just added the additive identity of this vector on both sides of this equation. So this gets killed and becomes the 0 of the vector space. This gets killed and becomes the 0 of the vector space. And by the property that the property of the additive identity, this is just 0 dot v. So the upshot is that if you scale any vector by the 0 of the field, you get the 0 of the vector space. Now again, this is an abstract definition. This quadruple, so many axioms, scary when we first see it, but really one should look at examples to understand what's going on. So here is our first example. R to the n. So let me do it this way. So consider R to the n. So what is this set? This is just all n tuples of real numbers. So once we are given a positive integer n, we can form the set Rn, and we define addition. We define a function which takes a tuple comma another tuple to the component-wise addition. This addition is something that we are defining, while this addition is the usual addition of real numbers. And of course, this is an abuse of notation, but this is a good abuse, because every time if we put subscripts here or design a new symbol for these things, then it will get messy. And really, it is a kind of addition, so it's good to make this kind of abuse of notation. That's completely acceptable. So we define it this way. Basically, another way of writing this is that you have x1 up to xn. This is first element of Rn, second element of Rn, and the resulting thing is obtained by adding component wise. So we define addition this way, and we define multiplication. R is a field, as we already discussed. We define this function which takes a real number. Let's call that alpha. Usually scalars are denoted by Greek letters. And you take any n tuple, and we just scale component wise. So this is just the usual multiplication of the two real numbers, x1 and alpha, and so on. This is how we define scaling. And one can check easy to check. That Rn with the addition defined above, okay, Rn with the base field R and the addition defined above, the multiplication defined above is a vector space. In fact, in exactly the same way, you can form this vector space, and you can form this vector space. And in fact, if F were some arbitrary field, you can form this vector space. We just write Rn for this as a shorthand. And from the context, it will be clear when we are thinking of it as a vector space and you're not thinking of it as a vector space. This, we just write Cn. This, for this, we just write Qn, and this, we just write Fn. So these are the most basic fundamental examples of vector spaces. And yeah, one should check that, yes, these are indeed vector spaces. One should check that all of these axioms are satisfied. This is the only way to get comfortable with these objects. So one should make that check. It looks a bit tedious, but one should do it. And just before we proceed, let me mention that what is R2? R we picturize as this, of course. With, let's say this, put a 0 here. R2 we picturize as our usual high school kind of plane. So these are the points of R2, all of these. This is the origin, the 0 of R2. And one can add, how do we add vectors? So for instance, let me make a bigger picture. Suppose we are given two vectors. Suppose I have a point in R2 here and a point here. Let's call this point U and let's call this point V. These points are vectors. In high school, we are usually taught that a vector is something that has a, I don't know, direction and a length. Yeah, but that's not the way we think of vectors. Vector, after all, is a point in R2. It's fine to associate this arrow to this point U. There's nothing wrong with it. But conceptually, the way we have defined things, this point itself is a vector. This point is a vector, this point is a vector, every other point here is a vector. And when you work out this coordinate wise addition, you will find that the resultant is the thing that you obtain by parallelogram law. So this point has the property that it is obtained by drawing a line parallel to this one and the line parallel to this one. The intersection of these two lines will yield this addition. So the parallelogram of vector addition that we learned in high school is precisely this coordinate-wise addition that we described. So this picture is useful for developing intuition. After all, we don't think in abstract symbols. We think, or at least most people think, in terms of pictures. And I'm not saying that that's the only way to think. There are sometimes formal ways to think, and not every time one can think in terms of pictures, but to develop some intuition and expectation as to what could be true, what could not be true, one needs to work with concrete examples. R3 is just your usual in the high school picture of 3D space. Any point here is a vector, and we add them just like we added them in high schools. That's the definition of a coordinate-wise addition. Okay. It's difficult to visualize C2, for instance. There's a good reason why we can't visualize it. It's a quote-unquote four-dimensional object. This, of course, is then even harder to visualize. But conceptually they are completely fine, these objects. All right, so these are basic examples. Let me give a few more examples and then we'll finish this lecture. This is the ring of polynomials. So again, let me start with the real numbers. Let n be a positive integer. A polynomial of degree n over R is a sum where these are all real numbers. X is a variable, whatever that means. An is non-zero. The degree is n, and that's basically the highest non-zero coefficient. So that's what a polynomial is. Formally, really, it's a list: a0, a1 up to an, just these n numbers. But when we think of polynomials, we don't think of them as lists. We think of them as objects like this. Uh, we write Rnx as the set of all polynomials of degree at most n, to denote the set of all of degree at most n. So this is just a set. This guy is just a set. We add two polynomials as follows. Suppose I have this polynomial. So this is a polynomial of degree at most n. And we add to another polynomial. So this is defined to be equal to. This addition should not be confused with this. These are anyway just formal additions, and we are defining another one by collecting the coefficients. It's really just the coordinate-wise addition in a disguise. We define addition like this, and we define scaling as you would expect. Alpha, okay, let me not write alpha, perhaps. Let me write alpha. Alpha is in the real numbers. These AIs are also in the real numbers. And this we define as this is defined to be like this. And again, one can check that R and X with base field R, the addition as defined, the scaling as defined, the vector space. Vector space over the base field R. And one can play the same game for complex numbers. Sorry, this is for rational numbers, and in fact for any field, finite field, whichever field you like. And again, we just simply write Rnx or Cnx, Qnx, or Fnx to denote these things. I don't think this is the standard notation. This is just notation that I've come up with. So please forgive me for causing any confusion. So these are other examples of vector spaces. Of course, you can see the similarity between this example and the previous example. It's really just a change of, instead of writing things as lists, we have just included these artificial things in between. But that's okay. We'll see how, in a precise sense, these are the same examples later. Another example is the following. Let X be any set, and let so V be the set of all maps from X to R. Just any map from X to R, we put that in V. So V is just a set, and here is, so we equip it with this addition. So if I have a map F and I have a map G, then I get a map which we denote by F plus G. And what does F plus G do? F plus G takes an element little x and spits out this sum. This is a valid sum. This is a real number and this is a real number. So we have just added those two real numbers. So F plus G is defined as the map from X to R, which consumes little x and produces the sum of the two real numbers produced by F and G. So that's how we add two functions. This is point-wise addition of functions, and scale. So we scale again in a very natural way. Produces a function which we write as alpha f, and what does it do? It consumes little x and produces alpha fx. Alpha is a real number, fx is a real number. We have just multiplied these two real numbers. This is a point-wise multiplication, if you will. Oh no, I shouldn't call it point-wise multiplication. That means something else. This is how we scale a function. And again, one can check that this is a vector space. Again, this game can be played for complex numbers, for rational numbers, or let me just directly skip to any field. And the same story, instead of writing this whole quadruple, we just write this, and it is understood from the context when we think of it as a vector space. So these are a few more examples of vector spaces. Let me give one more example, and then we'll discuss one more concept, and that will be it. So this example is coming somewhat outside of linear algebra. If you don't follow this, that's completely fine. If you follow this, that's great. But this is really optional. So let X be a topological space. Then CXR, or rather let V is equal to CXR be the set all the continuous functions from X to R. So we've collected the set of all continuous functions from X to R. That's why we need a topological space. From a set, we can't define a continuous function. We need a topological space to define a continuous function. We collect the set of all the continuous functions, and this is a vector space under a pointwise addition and scaling of continuous functions. So V, along with the base field R and the pointwise addition and the scaling, just like we did for this maps X to R, is a vector space. If you had a smooth manifold, then you can do the same thing. You can collect smooth maps, and then that is also a vector space. Instead of R, you can put C here. C also allows for continuous functions. We can talk about continuous functions from a topological space to C. So that is also that will also form a vector space that over complex numbers, in fact. So yeah, so these are some more examples. One specific instance of this example is just take X as the unit interval. But that's as much as I would like to say about this one. And now let us discuss the notion of subspaces, and that will be it. So let V be a vector space. Again, by this we really mean we have a vector space V, we have a base field F, we have addition, we have a scaling, but we just, by abuse of notation, replace it by V. So we have a vector space V over a base field F. Good example to keep in mind is Rn over R. And suppose we have a subset. Let S be a subset of V. Now we want to define the notion of a subspace. So we would like to call S a subspace of V if it becomes a vector space in its own right in a natural way. What do we mean by that? We say that S is a subspace of V if A plus B in S for all A and B in S. So first of all, it should be closed under addition. Meaning if we add two things in S, we don't get out of S. So of course we remain in V, but we insist further that we should again get back an element of S. And alpha dot, let me not write A and B. This is bad. U and B. Notationally, this is better. Alpha dot U is in S for all alpha in F and U in S. So again, this is closed under scalings. If we take a vector in S and scale it by any element of the field, the base field, we get back an element of S. So if this happens, then we call S a subspace. So one can check that if, in fact, one should check that S along with F along with the restricted addition is a vector space. So these things, this plus now denotes this map, and this as since S satisfies this property that if you add two things in S, you again remain in S. This map is indeed a map from S cross S to S rather than V. And similarly, this guy means the map which goes from S cross S to S. And again, by this property, this is a meaningful map. So basically, yes, we call a subset a subspace if it becomes a vector space by borrowing addition and scaling from the parent space V. And yeah, so that's a subspace. So let me just give one example. In fact, it's really an exercise. Show that the only subspaces of R. So R is a vector space. R is a field, but it is also a vector space over itself. R is a vector space over R. It's basically R to the 1. We discussed R to the n. This is R to the 1. The only subspaces of this vector space are the trivial one and the entire vector space itself. The subspaces of R2 are precisely of three kinds, precisely the following. So either it's the trivial subspace, or it's lines passing through origin, or it's the entire R2. If we draw a picture, this is a subspace of R2. Any such thing, any such thing is a subspace of R2, and of course the entire this R2 is of course a subspace of R2. So these are the only subspaces of R2, and it is a good exercise to in fact prove that this is indeed the case. These are the only subspaces. And what about R3? What about R3? So yeah, so I leave with this exercise. Next time we will discuss bases and dimension, linear independence, very important concepts. Okay.